Hi everyone, welcome to our 12th lecture. This lecture is on the conservation of energy for a simple harmonic oscillator. And since it contains calculus, this lecture is for the calculus students only. Okay, so let me remind you a little bit of what we've been doing with energy. And then during this lecture, I'll apply that theory to the conservation of energy in a simple harmonic oscillator. So last lecture, I showed you that it's possible to use Newton's laws to solve certain problems where the intermediate path between the initial and the final condition is actually irrelevant. Okay, and we looked at that for a specific case for the roller coaster, and what came out of that was an illustration, although not necessarily a proof, of the work energy theorem. And what the work energy theorem says is that if you do a total work W on some system, then that total work is going to lead to a change in the kinetic energy, where the work for a particular force is calculated by the force times the distance over which it acts multiplied by the cosine of the angle between the force and the displacement. And the total work would be then the sum of all of those works for each of the individual forces that are acting. And the kinetic energy is 1/2 mv squared. Okay, so if you calculate the total work done on a system, that's going to equal to the change in the kinetic energy, and the change in the kinetic energy would be you calculate 1/2 mv squared at the end and 1/2 mv squared at the beginning, and the difference between the two is the change in the kinetic energy. Now the work energy theorem works everywhere, it's applicable everywhere, but it's not exactly conservation of energy. It's heading there. Inside the work, because it's a total work, there can be work due to different forces. The work due to friction is problematic, and the reason it's problematic is because friction actually converts energy into heat. Now heat is a kind of energy, but it's not a kind of energy that we can handle right now. And so in systems where there's friction, it looks like the total energy isn't being conserved, but when in fact it really is. So if you take the total work and you split it into two pieces, a conservative work due to conservative forces and work due to non-conservative forces, then you can deal with the two pieces differently. If there are no non-conservative forces, in other words, there's no friction, because that's the only non-conservative force we have, then all your work is due to conservative forces. You could take that work and write it as a change in potential energy. Okay, and potential energy is the energy in a system because of the way it's configured. Okay, just meaning something like if you have a block and it's at a certain height, then that block has potential energy due to gravity, mgh. You lift the block and you let it go, it's going to do more work when it falls. Gravity is going to do more work on it. The block will do more damage when it hits the ground. So there's a potential energy in it, an energy which is stored inside of it. And for gravity, the formula there was mgh. It's the same with a spring. If you've got a spring and you compress it, then the spring, has some energy in it. And if you let go, boink, the energy will be released, and that potential energy is given 1 by 1/2 kx squared. So if all of your work could be written as just it was all due to conservative forces, that work could be written as a change in potential energy. And then rearranging things, you have that the total energy before would equal the total energy after, and that was conservation of energy. Where total energy now means the kinetic energy plus the potential energy at any point during the cycle or during the motion. Okay, and we're going to take that, we're going to take the conservation of energy, and we're going to apply it to a simple harmonic oscillator. And the reason we can do that is because in a simple harmonic oscillator, there's no friction. No friction means there's no work due to non-conservative forces, in which case the work energy theorem just reduces down to conservation of energy. Okay, so that's a little bit conceptually, demanding, but hopefully it'll become a little bit better. So because there's no friction here, it's all going to be conservation of energy, and you're going to see at every point I'll just invoke conservation of energy. Next lecture, we're going to bring in the complication due to friction. Okay, but let's start off. So what you're seeing here in my diagram is a simple harmonic oscillator. And when I first introduced the kinematics of simple harmonic oscillators, I wasn't worried about what was causing something to oscillate back and forth. I just said that there are a lot of things which vibrate, which oscillate back and forth. But now we're actually going to do a bit of the dynamics, okay? And so to get something to oscillate back and forth, we can use a spring, okay? So here's a spring, and it has a spring constant K. All right, and if you remember what the spring constant K is, that's how much force it takes to compress the spring by a certain distance. All right, and The uh, the oscillator is made up of a mass m like that. And this spring naturally wants to sit at equilibrium, which is my x equals 0 there. So if I just let the mass sit at x equals 0, the spring is neither compressed nor is it stretched. It would just want to sit there. Okay, so that's the equilibrium position. Now, if I take and I compress the spring, that's what my x looks. That's what my x is trying to indicate here with that arrow. So I've compressed the spring. What the spring wants to do is it wants to expand, and so it wants to push the mass back to x equals 0. Okay. Conversely, I didn't draw it here. If I stretch the spring, then the displacement would be out in the right, towards the right here, in the opposite direction that you see in the diagram, and the force would be back towards the equilibrium. Notice that the direction of the displacement, x, and the direction of the force are opposite one another. Okay. Now, there's a relationship between F and x, and that is Hooke's law, okay, which is right here. All right, basically F is equal to minus kx. Now, I actually wrote this in my previous lecture. I just mentioned it because I wanted to make the connection to what I was going to do in this lecture. But when I did that, I didn't have the negative sign in there. I wasn't too worried at that point about the direction. This negative sign simply indicates that x and F, the displacement, that is how much you've compressed the spring or stretched the spring, the direction of that compression or expansion is in the opposite direction to the force. Okay, so the force is always looking to move the mass back to equilibrium, hence it's called a restoring force. Okay, so the force is called a restoring force, and the entire law is known as Hooke's law, and you'll actually study that in the lab. Okay, and there you see K. Because after all, K was, how stiff the spring is, and it's basically a measure of like how much force does it take to compress it per unit meter, and you can see that right here because, if I compress it 1 meter, say K is 1 Newton per meter. If I compress it 1 meter, that takes 1 Newton. If I compress it 2 meters, that'll take 2 newtons. If I compress it 3 meters, that'll take 3 newtons. The ratio between the force here and x, that is K. Okay, so K is how much force does it take to compress it per unit meter, all right, per unit length in general. So there's K. All right, now at this point we can start to use Newton's second law, okay, with that force, with that formula for the force in there. So how would we do that? Well, remember Newton's second law basically says F net is equal to ma. Well, here's my ma, and on the other side I have to have F net, and you see that F net is exactly my my restoring force, and you go, well, wait a sec, isn't it supposed to be the net force? Yeah, it actually is just the restoring force. So I didn't do the free body diagram for M here. It's pretty easy. There's gravity down, but you know that the gravity down is going to be balanced by the normal force up, and so there is no force perpendicular to this tabletop. Okay, so there's no vertical force. Horizontally here, there's only one force, and that's the restoring force. So the net force is the restoring force. Okay, now I didn't write F equals ma or F net equals ma before this, but this side here, the right hand side, is F net. Okay, and the other side is the ma. Okay, I don't know why I switched the order here, but it doesn't matter. Basically, negative kx, there's your F net, and that's got to equal ma. Okay, now let me isolate a on this side here. So a is going to equal minus k over m times x. And remember from our kinematics that a is the second derivative of x, okay, because x is a displacement. It's basically a measure, along our ruler underneath the oscillator. Go back to the diagram here. Equilibrium is x equals 0. We simply chose the 0 of the ruler to be exactly where equilibrium is, and I didn't draw off all the markings here, but you could have like a 1 centimeter mark there, and a 2 centimeter there, and a 3 centimeter, and this would be -1 centimeter, -2, -3, and so on. Okay, and you'll actually, like I said, you'll actually do this in the lab. You'll do it on a linear air track, and the linear air track has a little ruler along the bottom, so you can measure x. Okay, now so x is basically the displacement from equilibrium, and the acceleration is the second derivative of the displacement from equilibrium. Okay, so this equation here for a I can write as d2x by dt squared, the second derivative of x. Okay, and that we know from kinematics. By definition, the acceleration is dv by dt, and v is dx by dt, and you put the two together and you get that a is going to be the second derivative of the displacement with respect to time. That's going to equal minus k over m, but I'm going to write k over m as minus omega squared, Hang on a second, you'll see why. And times x. Okay. Now, if I write uh, if I write omega squared for k over m, then omega must equal the square root of k over m. Okay, because if I put square root of k over m in there, then the square root goes away and I get k over m. Okay, so omega is equal to the square root of k over m. At this point, you'll go, well, wait a sec. Why did you choose the symbol omega? Couldn't you have chosen some other symbol there? I purposely chose omega because we're going to see in a second that this is the angular frequency. Okay, so you saw the angular frequency when I first introduced simple harmonic motion, but now I'm actually giving you something deeper. I'm giving you the dynamics of the simple harmonic motion, and you're going to see that the angular frequency is actually derivable from the spring constant divided by m, which we didn't have before. Before I had to just say, look, this oscillator has I could either give you the linear frequency, or I could have given you the period, or I could have given you the angular frequency directly, but usually I would give you period or linear frequency. But now I'm gone one step deeper. I can give you the spring constant and mass, and you can calculate the angular frequency from that. Okay, but let's see that it really is the angular frequency. So if you take a look at this equation here, this is what in mathematics is known as a second order differential equation, and the reason is that x is a function of time. So even though it looks like just x, it's not a number. Don't think of x as a number. Omega squared is a number, but x is a function, and x is a function here. So you know what this equation says? This equation says if I have a function and I differentiate it twice, I'd better get that same function back again with a minus omega squared in front. So let me say that again. This equation says find me a function x, a function of time, such that when I differentiate that function twice, I'm going to get the function back again, but with an omega squared in front, or minus omega squared in front. Okay, and you go, well, what function will do that? And we know the answer because we did this when we did the kinematics of simple harmonic motion. It's the cosine function, like there, right there. So x is equal to a cosine omega t. Okay, where omega here is obviously the angular frequency, because the angular frequency is that frequency for one oscillation of the cosine. Okay, so there you go. There it is. There's the interpretation of omega as an angular frequency, and a was the amplitude. If we differentiate it once, we get v is equal to dx by dt. Okay, so the velocity is the first derivative. If you differentiate this twice, I won't go through the details, but you get the sine with an and the a in front, that just carries over, but you get an extra minus omega in front. Okay, so v is minus omega a sine omega t, and then you differentiate it again, the sine becomes a cosine, and you get another factor omega in front. So now you got that a is equal to minus omega squared a cosine omega t, and you go, wait a minute, a cosine omega t, isn't that just x? And the answer is yes. So you could take that a cosine omega t, you could just take that out and put x there, and look at what we have. We have that a is equal to minus omega squared x. And that's exactly where we got to starting from Hooke's law. Okay, so let me just recap what we did here, because it's kind of compact, but it's actually pretty deep in terms of like what it's saying in terms of the physics. If you have an oscillator like this, where the restoring force, that is the force as you displace the mass from equilibrium, is just linear in x, which is basically Hooke's law, so F is equal to minus kx. Linear and in the opposite direction, you need that minus sign in there. Okay, so if you have that as a force, you have a restoring force. That restoring force, because it's a force, is going to lead to an acceleration. That acceleration, because the restoring force is linear in x, that acceleration is linear in x. Okay, and so basically you get that the second derivative of x is proportional to x itself, and the only function that when differentiated twice will give back the function again is the cosine or the sine, although we've been emphasizing the cosine. Okay, and so it's a sinusoidal function. Okay, and so basically this right here says that you must have a sinusoidal function. We've been picking on the cosine, and so there you go. There's the cosine. Okay, and what I basically did was show you that Hooke's law, a linear restoring force, gives rise to simple harmonic motion. Okay, so that's one thing that I showed you, and the other thing is we actually did get a new equation out of this. Okay, so it's not like this is just pure theory. You can actually make use of some of this in solving your problems, and it's this equation right here. If you look back at the stuff that I did on 1D kinematic simple harmonic motion, you won't see this equation, okay? Because I just said, look, oscillators do this. I didn't tell you why, okay? But now I'm telling you why. And remember that dynamics is an explanation why. So the angular frequency is actually equal to the square root of the spring constant, that is how stiff the spring is, and how big the mass is. And it kind of makes sense. The stiffer the spring is, the faster it'll vibrate back and forth, okay? And the bigger the mass is, the slower it'll vibrate back and forth, because the bigger the mass, the harder it is to pull it in and push it out. It's okay, like that. Okay, and so the angular frequency, you would expect it to increase with a stiffer spring, a bigger K, and you would expect it to decrease with a bigger M. The square root is a little bit counterintuitive, or not counterintuitive, but you may not have been able to guess that. But I certainly, omega is equal to the square root of K over M does make sense intuitively. Okay, and this comes up over and over and over and over again. In fact, a fun little party trick is you take a glass and you pour, wine or water or whatever fluid in it, and you take your finger and you dip it in the fluid, and then you run your finger along the top. If you've ever done this before, I'm sure there are YouTube videos that show this. The glass will start to ring, okay, and it'll go something like that, okay, and then you pour more fluid in and you do it again, and you'll notice that the frequency decreases. And you go, why is the frequency decreasing? Because the glass has a certain K associated with it. That doesn't change. You're not making the glass thicker when you pour the fluid in. No, what you're doing is you're making the mass of the vibrating material more, because there's now not only the glass, but there's more fluid that's vibrating. And the more fluid is vibrating, the more mass is vibrating, the lower the frequency is going to be. And try this. It's kind of a fun little trick to do. So I don't know. That's just like one illustration of the intuitiveness of this particular formula there. Okay, let's return to our analysis of the simple harmonic oscillator. So we got one equation. The omega is related to K over M, just like I said, but there's more. And remember, we're heading towards energy. So here I've got a full cycle of the simple harmonic oscillator, okay? So remember, it's 1D, but I can't really draw a 1D, cycle back and forth. So I kind of expanded it a little bit here. But imagine that you start here at point A, okay? So here you are at point A, and, x equals 0 is in the middle. At point A is going to be the amplitude. So this is x equals A at point A. And then, of course, the oscillator is going to start to move, and it accelerates until it passes equilibrium. Equilibrium is point B. And then it passes this arbitrary point C, which I'll refer to later. Okay, and then it stops at x is equal to minus A, which is the amplitude on the other side. That's as far as it's going to go to the left, okay? And the velocity is 0 there, right? And then it passes through equilibrium again. And at equilibrium, x is equal to 0, but remember, the velocity is your maximum. Okay, so at equilibrium, that is point B, at equilibrium, x is equal to 0, velocity is maximum. At point A, which is where you've reached the maximum displacement or your amplitude, x is equal to A, but the velocity is 0, because that's where it stops and turns around. Okay, now I said that before when we did the kinematics of simple harmonic motion, 1D simple harmonic motion, but now we can think about this in terms of energy. Okay, when you are at maximum displacement here, that's x equals A, all right, your velocity is 0. Velocity 0 means that the kinetic energy is 0, because the kinetic energy is calculated as 1/2 mv squared. V is 0, v squared is 0, 1/2 mv squared is 0. There is no kinetic energy at the endpoint here, A. Conversely, at the other end, there's also no kinetic energy. So at the endpoints, there's no kinetic energy. All the energy, because the oscillator does have energy, otherwise it wouldn't move at all the energy is potential. So at these endpoints here, all the energy is potential. Okay, let's look at equilibrium. At equilibrium, x is equal to 0, because the spring is not stretched at that point. I know that's only going to last for an instance, because the oscillator is passing through 0, and the mass is passing through 0. So one instance the string is stretched, the next instance it's compressed a bit, and so only for that instance at x equals 0 is it actually not compressed. But it's not compressed at that instance, and so when x is equal to 0, there's no potential energy. Okay, because the potential energy for a spring is calculated as 1/2 kx squared. I didn't prove that to you. I'm not going to prove it to you, but it kind of makes sense, because you see, if the spring is not stretched, x is equal to 0, there's no potential energy. The more you stretch the spring, the more potential energy there's going to be. It turns out to be an x squared, okay, and you actually have to do integration to do that, so I'm not going to prove that to you. But yeah, there's an energy, and it goes as x squared, okay? So when x is equal to 0, there is no kinetic energy. Sorry, when x is equal to 0, there's no potential energy. It's all kinetic energy. And in fact, V is your maximum value, okay? So at equilibrium, you've got all your energy in kinetic, calculated by 1/2 mv squared, where V now is V max, and you can even say the energy is 1/2 m v max squared, okay? And at the endpoints, it's all potential, and you could actually calculate it as 1/2 kx squared, but x is equal to a, so you could actually say 1/2 ka squared, okay? Now at an arbitrary point, you can't say that it's all kinetic or all potential, because let's just go through the cycle. We start here, all potential energy. We get to B, it's all kinetic energy. In between, what happened? It transitioned between all potential to all kinetic. Okay, so here you're all potential, here you're partially potential, partially kinetic, and there you're all kinetic, and then here you're all partially kinetic, partially potential, and then there you're all potential, and so on and so forth. Okay, so you can see that as the oscillator goes back and forth, that the energy sloshes back and forth between all potential, all kinetic, all potential, all kinetic. Once again, at the endpoints here and here, all potential. In the middle, all kinetic. At some arbitrary point, a little bit of both. Okay, how much of each? Well, it depends. The closer you are to an endpoint, the more it's going to be in the potential regime, and the closer you are to equilibrium, the more it's going to be in the kinetic realm. Okay, so let's make that into equations. So at point A, all the energy is potential energy, and that's calculated by 1/2 kx squared. But you'll notice that I took out the x and I put in a. Why? Because x is equal to a at the endpoints. So the energy, if you want the total energy, you can use the formula 1/2 ka squared. Okay. Conversely, you could calculate the total energy at B, and the total energy at B is going to be 1/2 mv max squared. Okay. Again, it's 1/2 mv squared is how you calculate the kinetic energy, but V at x equals 0 is V max, and so you get that. Okay, and I'm actually going to show you that these two are the same as one another. Okay, so let me show you that. Remember from our kinematics, we had that Vmax is equal to omega A. All right, and if you don't remember that, we'll go back and take a look. But yeah, if you have A, the amplitude, and you have omega, that will tell you Vmax. All right, and for omega now, we're going to replace that by the square root of k over m. Okay, so start with the formula at equilibrium, which is E is equal to 1/2 m v max squared. And for V max, let's replace V max with the square root of k over m times A, like that. Well, distribute the square root of k over m is just k over m. A squared is A squared there, like that. And then notice that the masses will cancel there, and we get 1/2 ka squared. So starting from 1/2 m v max squared, we were able to show that that's equal to 1/2 ka squared. All right, and that's exactly what you expect. Why? Why do you expect these to be the same? You say, well, this is at the endpoints and this is at equilibrium. Yeah, but it's the energy. This is the energy calculated at the endpoints, and this is the energy calculated at equilibrium. But the energy, there's no friction here. The energy is conserved. So these two numbers had better be the same. In other words, in a problem, if I give you A and K and you calculate the energy, you get a number. If I give you Vmax and M, you calculate the energy, you get a number. Those two numbers, if they're applying to the same oscillator, they had better be the same. Otherwise, energy is not being conserved. Okay, so these two are the same, and I actually proved that right here. Okay, starting from 1/2 m Vmax squared, I was able to show that it's equal to 1/2 ka squared. All right, at point C, you can't say the energy is all kinetic and all potential, and you can't say x is equal to A or V is equal to V max or anything like that. So you just have the generic formula like that. E is equal to 1/2 mv squared, which is your kinetic piece, plus 1/2 kx squared, which is your potential energy piece. Okay. Now, because of conservation of energy, all three of these formulas had better give you the same answer. Okay. And you say, but they're being calculated at different points in the cycle. I know. But that's the point of conservation of energy. Whether you calculate that energy at the endpoints, which is this one here, the first one, or you calculated equilibrium, which is the second one, or you calculated at some arbitrary point, which is your third form. All three of those had better give you the same number, okay? Because energy is conserved, no friction, no non-conservative forces, so energy is conserved, okay? So I didn't do this. I could have actually done yet another demonstration here to show that these are all equal to one another. I just asserted that this last piece is equal. I actually proved that these two were equal. But you can even prove that this third piece is equal to the other two. And you say, how do you do that? See V there? You just go back to here, to your formula for V. V is equal to minus A omega sine omega t. And then you also had x in there. And for x, you use A cosine omega t. And so in this formula down here, in the V squared, you're going to have a sine squared. And for the x squared, you're going to have a cosine squared. And sine squared of an angle plus cosine squared of the same angle is equal to 1. And that drops out all the time dependence in this piece. And guess what? Depending on how you massage the arithmetic, you'll either get the second form or the first form, okay? I didn't want to do that. I don't think it gives you that much extra information. You have to use this trig identity, cosine squared theta plus sine squared theta is equal to 1. But yeah, it's easy to prove that all three of these are equal to one another, okay? So this is the end of the theory. Let me just summarize the formulas before we jump into our first examples. Our first example. So here, basically, we have the energy, and there's three ways to calculate the energy, as we just discussed, okay? Omega, not explicitly here, but omega, the angular frequency, can be obtained from the spring constant and the mass by this formula, square root of k over m. And finally, what does omega mean? Well, omega is 2 pi over the period, where the period is the time for one cycle, or omega can be written as 2 pi times the linear frequency, okay? And in a lab, you don't measure omega directly. You measure the linear frequency directly. That's like in 1 second, how many times does this oscillator bob back and forth? Okay, if it's a fast oscillator, it might bob back and forth 10 times in 1 second, in which case its frequency is 10 hertz, 10 cycles per second. That would be the linear frequency, okay? The period is how long does it take a cycle? So in my previous example, that would be like 1 cycle would take 1/10 of a second, so it would be like 0.1, okay? And omega has this extra 2 pi in it because of the sines and cosines, okay? We went through that before, but just to remind you. These are all the equations that you really need to solve these problems. Okay. Let's do an example. One is sufficient here. So I have a spring, and it has a spring constant K of 100 newtons per meter. What does that mean? To squish this spring by 1 meter, I need 100 newtons. Conversely, to stretch the spring by 1 meter, it would take 100 newtons. Okay, so a spring constant has K equals 100 newtons per meter, and we attach a 1 kilogram mass to it. All right, so that's my M. All right. We start the system oscillating. So, it's just sitting there, and I'm going to give it a tap, and it's going to start to oscillate back and forth. So the first question I ask is, what is the period of the motion? So basically, I want t. And looking at our equations here, you go, well, there's really only one equation for t there, and it's in terms of either the angular frequency or the linear frequency. And did I give you enough information to get the angular frequency? And the answer is yes, because I gave you, let me just scroll back, because I gave you k. All right, I gave you k, and I gave you m. All right, omega is equal to square root of k over m. That was easy. You just put in k is 100 newtons per meter, m is 1 kilogram. Take the square root of that. It turns out to be 10 per second, or 10 hertz. Okay, so that's the angular frequency is 10 hertz, but I want the period, and up above I wrote omega is 2 pi over t. But if I multiply both sides by t and divide both sides by omega, this equation is the same as t is equal to 2 pi over omega. Substitute the 10 in there. 2 pi divided by 10 is 0.628 seconds. Okay, so that answers the question. The period of the motion is 0.628 seconds. All right, before I move on to part B, just to show you that the units work out, I actually wrote in the units here in the formula as I solved. So here I have K, and I replaced it with 100 newtons per meter. Okay, so on top we have a newton per meter, and the mass m was 1 kilogram. Do these units actually work out to per second? Okay, so a newton, just to remind you, a newton is a kilogram meter per second squared. Okay, so newton, just think of F equals ma. Newton is an F, m is kilogram, a is meters per second squared, so a newton is a kilogram meter per second squared. Great, but that's not K. K is not in newtons. K is in newtons per meter. So divide out a meter there. So here's Newton. Newton divided by a meter. That gets rid of the meter. You just get a kilogram per second squared. Okay, so the top is a kilogram per second squared. A Newton meter is a kilogram per second squared. Okay, now divide out the kilogram there, and the kilogram goes away, and we get a per second squared. And that per second squared, though, is under the square root. And so per second squared, square root is just per second. Okay, and there you go. The units work out. All right, great. So there's part A. All right. And part B here, we give the mass an initial push so that an initial push so that its initial velocity is 2 meters per second. Okay, I should probably have said here, and on a test, I'm very careful with my language. Okay, because we're doing this together, it can be a little bit more casual. But I would have said at equilibrium, and it starts at equilibrium, and I give it an initial velocity of 2 meters per second. Okay, so so we're at, just picture it, it's at equilibrium, and I give it a tap such that its velocity initially is 2 meters per second. Okay, find the total energy and find the amplitude of the motion. All right, so the reason I was very picky about, where is this initial velocity 2 meters per second is because if you say that it's 2 meters per second at equilibrium, remember at equilibrium, that's where Vmax occurs. So to say that the velocity is 2 meters per second at equilibrium is to say that Vmax is 2 meters per second. So that's why it's important to know that Vmax occurs at equilibrium and Xmax, or in other words, the amplitude, occurs at the endpoints, okay? Because I may not say to you Vmax is 2 meters per second, and no problem, I might just say to you, we find that the velocity is 2 meters per second at equilibrium. I might just say that and expect you to know that Vmax, that means that Vmax is 2 meters per second. Okay, so if we have that Vmax is 2 meters per second, we've got everything to calculate the energy using which one? Well, we have Vmax, we have the mass, so we use the second form here. Okay, so E is equal to 1/2 mv max squared. Okay, that's the total energy. The total energy is all kinetic at equilibrium. There's no, the potential energy, if I were to write it in there, would be plus 0. Okay, and so we have 1/2. The mass was 1 kilogram. Vmax is 2 meters per second, and so the total energy is 2 joules. Okay, and we could either at this point use Vmax is equal to omega times A to get the amplitude, because that's the next thing I wanted. So one of the questions was, what's the total energy? That answers that, 2 joules. The other part was find the amplitude. We could use Vmax is equal to omega A for the amplitude, or since we're doing energy, let's use that E is equal to 1/2 Ka squared, okay, to get the amplitude. Why? Well, because now we know the total energy, it's 2 joules. And we know K, I gave that to you, 100 newtons per meter. We can calculate A, okay? So starting from E is equal to 1/2 Ka squared, substitute into numbers, 2. Remember, the energy is the same throughout the cycle. So don't get confused. Before we calculated equilibrium, here it's at the endpoint, same energy though. So E is 2 is equal to 1/2, K is 100. A is unknown, that's what we're solving for. And just rearranging that, I get that A is equal to 0.2 or 20 centimeters, okay? So 0.2 meters or 20 centimeters. So as this oscillator oscillates back and forth, here it is at equilibrium, it'll go 20 centimeters to one side and it'll oscillate 20 centimeters to the other side around equilibrium, 20 centimeters on each side of equilibrium. Okay, great. And here's another question. How fast is it moving past, how fast is it moving when it passes x equals 10 centimeters, okay? So we know that its maximum displacement is 20 centimeters on either side. And what I'm asking for now is how fast is it moving? In other words, what's its velocity when x is equal to 10 centimeters? Now think to yourself, where is x equals 10 centimeters in the cycle? Well, it's not x equals 0, so it's not equilibrium. It's not x is equal to 20 centimeters, so it's not x is equal to A. We're actually at halfway between x is equal to A. This is like my point C up here. So in this problem here, or in this diagram here, A is when x is equal to A. Point B is at equilibrium. Point C is like the question we're looking at right now, okay? You're at x equals A. You're not all the way to the x equals 10 centimeters would be here. X is 20 centimeters would be there, okay? So you're like halfway, all right? So you're neither all potential nor all kinetic. You're a little bit of both. And that tells you that you need to use this particular form right there. Okay, so let's go back to the question again now that we know how to tackle it. And the question was, how fast is it moving? In other words, what's the velocity when x is equal to 10 centimeters? We know we have to use this form right here because we're at neither extremes, neither all potential nor all kinetic. And let's start. So for the energy, it's still 2 joules because it's 2 joules everywhere in the cycle, okay? 1 half m is 1. V, we don't know, so leave the v squared alone, okay? Plus 1 half, k we know is 100, and x, I told you, it's 10 centimeters, but we need it in meters, so it's 0.1 meters. That's where that 0.1 came from, okay? Take a look at that after we substituted in the numbers. The only unknown is v. Great, so the rest of it is just reducing. So 2, 1 half v squared, and then all of this just works out to 1 half. 100 times 0.1 squared, 0.1 squared is 0.01, times 100 is 1, so you just get a half. And what I do here, just multiplied it through by 2, so I get 4 is equal to v squared plus 1, and that means that v squared is 3, or v, if you take the square root of 3, is 1.73 meters per second. Okay, so there you go. There's an example which still illustrates all of the points to how the energy evolves as an oscillator uh, oscillates back and forth. Okay, um, the theory is a little bit more conceptually demanding, but the actual application of the formulas is pretty easy. The only mistake I've seen students make in the many years that I've taught this is generally in doing this. For some reason, even though you know that energy is conserved, when you are at a particular point in the oscillator, you say, "Well, I need to calculate this at equilibrium, so I need to use this, but I don't have V max. What do I do?" Remember, you don't have to calculate the energy at the point in which you're of interest. You could calculate the energy anywhere. So you might be interested in the energy at equilibrium or the velocity at equilibrium, which is this, but you may have the information to calculate the total energy at maximum displacement. And that just seems to cause some confusion. Don't let it, okay? So just think to yourself, can I get the total energy anywhere? Just like look along the thing and say, can I get the total energy anywhere? And the answer is yes. And if you can, then you've got E, and then, it usually leaves just one unknown, okay? Well, that's it. Thank you very much for listening.